If you've ever had to stop suddenly while driving at high speed, you know that once you hit the brakes, they can easily lock up, making you skid. But with the sophisticated computer technology behind today's anti-lock brakes, skidding is becoming a thing of the past. Brakes are absolutely essential equipment for every vehicle to slow down and stop. And brakes have remained practically unchanged for the past 40 years. Conventional disc brakes have pads that press against the brake disc, attached to the wheel. These pads grip the disc on only 15 to 30 degrees of its circumference. This develops high heat, wheel skidding, and results in premature wear. The new floating disc brakes have two pads of friction material on 360 degrees of the disc. When the brake is applied, hydraulic pressure activates the diaphragm, which applies pressure on the inboard pad, which is then pressed against the disc. In this animation, the diaphragm movement is exaggerated. However simple, the design of this brake calls for some complex development steps. It all starts on the monitor screen with computer-aided design. This powerful software creates objects in 3 dimensions, which can be virtually manipulated. They then proceed to digital analysis. Here, digital models are submitted to repeated braking to verify that the parts conform to design objectives. The software verifies changes in heat, the effects of vibration, and resistance to breakage. The right choice of materials is critical. The electrical components also have to be created. Here we see the delicate construction of tiny sensors that measure the force exerted by the braking system. The sensor is the main component of the intelligent ABS braking system, which functions more efficiently than traditional anti-skid systems and reduces braking distance. Next, it's the fabrication stage of prototype parts which will be tested. The machining of these parts must take into account the requirements of mass production. This high-precision robotic machining is done by computer-controlled digital machines. A liquid sprinkled on the machine part cools it during the process. The finished parts are precisely measured, then fitted and assembled to form the total braking system, which will be first tested in the laboratory. Brakes in full contact have a friction surface 6 times superior to traditional brakes. The use of aluminum and composite materials allows for a weight savings of 5.5 pounds per wheel. This affects road holding and reduces fuel consumption by 0.05 gallons per 100 miles. They proceed to power and endurance tests on this dynamometer, in which a brake and wheel assembly act against a large rotating drum. These lab tests are critical since they can detect any defect in a braking system before it's installed on an actual vehicle. In order to evaluate the power and endurance of the brakes in full application under extreme conditions, they were installed on this Porsche 911 Turbo, entered in the Motorola Cup. They proved completely satisfactory, and the Porsche went on to record many wins. Once all validation tests are done, we move on to the next step. Brakes are installed on a production model vehicle. With data systems, engineers can observe the performance of brakes under all conditions, thousands of times a second. Finally, engineers proceed with actual braking trials with test vehicles. All that remains is to produce brakes on a large scale to supply auto manufacturers' production lines. And that's the story of brakes, from original idea to final product.